2017. During that time, Joe has worked to develop mold and color, Class A, and structural SMC formulations for the automotive and heavy truck markets. Joe received a bachelor's in chemistry from Ohio University in 2013 and is currently pursuing a master's in applied statistics from Penn State. Joe?
Hi everyone, thank you for being here. I presented virtually last year, so this is a little bit more welcoming, I think. But without any further ado, let's go ahead and talk about accelerated weathering tests and materials. So first off, and I'm sorry because our keynote speaker probably gave you a little bit of an overview on this today, so there might be a little bit of a repeat. But what is Ineos Composites? We used to be Ashland Composites, which I'm sure a lot of you are more familiar with. But Ashland, or now Ineos, sells vinyl ester resins and unsaturated polyester resins and gel coats for a variety of composite applications. I, as I was introduced as, work specifically in the transportation division. So as you can see here, it's a SMC made truck part that we have on display in our facility. But Ineos makes a whole bunch of composite resins for brands like Aerotrain and Duracane, and a lot of other things. If you want to learn more about our products, feel free to stop by our booth. And we have a world-class R&D center in Dublin, Ohio, where the work that's going to be presented today was conducted at. And in that in that R&D center, we have accelerated weathering units, specifically QUV units and xenon arc chambers. And so the tests that I am going to discuss later were all conducted there. And what are we going to talk about today? So the goal that we set forward when we started this project is we want to learn more about accelerated weathering tests. So mold and color, which I'll talk about what exactly that is in a second, requires special types of testing that thermoset composites normally don't see. So there's a couple different ways you can do this test, and we were wondering what are the differences between these tests, how do our products perform, and how can we eventually make recommendations to someone that might be formulating an automotive composite about you want to do this test for this reason, and then if you see these results, you can probably say it's going to act this way out in the field. So that was our goal, and yep, that's what we're going to talk about. Oh, and we did this by looking at 3 different types of SMC formulations, which I'll also talk about in a second. So we looked at 3 different SMC formulations by 3 different methods, and we're going to compare and contrast. And what are mold and color composites? So normally we have this part on display out in the lobby, but unfortunately I guess we didn't ship it up today. But mold and color composites mean that the color is molded into the part. So a lot of times you'll paint an SMC composite black or something like that, as I'm sure you've all seen from Class A parts. But when you put something like carbon black directly in the composite, you can get a nice black color where you don't require an exterior paint step or secondary paint step, and you can imagine why that might be useful. You're simplifying the process, you eliminate a environmentally unfriendly paint step, and then just by simplifying, you're going to reduce cost. And there's some other advantages from using mold and color composite, but one of the neat things is you can now make exterior parts that a customer will see without going through a paint step. So as you can imagine, this requires good parts that look nice, and also since they're going to be an exterior application, they are going to be exposed to the elements, that is the test that we're going to be talking about today, is how do you test these exterior weathering tests, and how do you prove that something will stand up to the Florida sun or the Michigan winters, and so on. So these parts were first introduced and kind of proven out in a commercial setting through the Honda Ridgeline. So if you look at a 2017 and forward Honda Ridgeline truck bed and truck tub, those are actually all made out of glass fiber reinforced resin systems. And so the resin was supplied by Ineos Composites. The resin brand is Aerotrain 805, but it kind of shows you don't need to make a truck bed out of metal. You don't need to make an exterior part out of metal or a composite that's been painted. You can do it directly with just a one-piece, one mold solution, where this entire part that I'm showing here is about 4 different parts, but it required no secondary painting, and the only joining together was the adhesive, which our friends at Ashland Adhesive, I'm sure, would love to talk to you about as well. And then, as I mentioned earlier, these mold and color parts have specific needs for testing. So most parts, like I said, most SMC parts that is, don't undergo exposure to the elements. They are just, in an interior application where they're not going to see the sun or UV or humidity or anything like that. So how do you actually prove out that these things will last 10 years out in the field, right? Because this is a truck bed, people will use this part hopefully as a work truck, so we want to make sure it continues to look acceptable as it gets used. So there's a couple different ways you can test this. The kind of gold standard by OEMs is to actually stick it out in the Florida sun and see over the course of 2 years, how does the color change, how does the gloss change, and that's all well and great and the preferred thing to do, but the problem is that takes 2 years. So I looked at two other methods, QUV and xenon arc, and those are the methods I tested them by, to try and figure out, can we understand if a composite, can we understand the performance of a composite in less than 2 years? Can we do an accelerated method that will accurately emulate how it will perform out for these 2-year-long exposure tests? So QUV is a trade name, by the way, it doesn't mean too much, but that uses the UVB light spectrum. So if we remember our physics classes, right, like light is a spectrum, or light has a certain wavelength, and that wavelength is a certain amount of energy. So a spectrum of light has many different wavelengths, and that is what kind of distinguishes these two different tests. So the UVB lamp, as you can see in this graphic I showed to the right, is contrasted with the first kind of hump U-shaped line contrasted to the squiggly line next to it, which is the sun. So if you look, the UV light from the UVB lamp shows a shorter wavelength, so a smaller wavelength, than compared to the sun, and this means it's providing a more intensive wavelength of light when compared to natural sunlight. But that gives you some advantages, but it is different than what sunlight will provide. Then xenon arc, much like QUV, provides another spectrum of light, but this light is more closely related to the natural sunlight. So a xenon arc lamp hopes to emulate more closely what exactly the spectrum of light that the sun will provide. And both of these QUV and xenon arc testing procedures both have heating elements to them, 70-degree heat cycles, in either a condensation cycle with QUV or 50% relative humidity cycle for xenon arc, hoping to naturally emulate rain and morning humidity and those sorts of things. So these are the three methods that we looked at for the purposes of these tests. And so for outdoor exposure, what we actually did is we sent them out to an outside testing lab, and they were tested over the course of 2 years in Florida with measurements given every 6 months with their color change. So we looked at 3 different formulations for this experiment, formulation A, B, and C. A and B were based off Airtran 805, which is the resin system that is currently in use for the Honda Ridgeline. So this is a proven resin technology. It's currently being used in the field. Formulation A is something that can be thought of as a control. It's one of our more standard formulations that's been vetted out before and has been proven to work in the marketplace. It's a standard density resin, kind of for standard density run-of-the-mill applications. Our next formulation was formulation B, and that was a special version of Airtran 805, specifically formulated for 1.6 density SMC applications. Then our last formulation is something new that we're working on and that we consider our next generation technology. So this is kind of molding color technology 2.0. So formulation C was based around Airtran 2805 as the resin system, and this system is meant for higher performing applications. By higher performing, we mean higher strength, higher weathering resistance, and applications that require a better look to it, so we consider them to have better color uniformity. So our speculation when we started this experiment was that Airtran 2805 or formulation C would perform the best out of the 3. And before we get into this, just in case anyone doesn't know, when we talk about color, of a composite, there's a couple different ways to talk about it. What we're going to be focusing on here is the LAB measurement system. So LAB means there's three different coordinates of, three different measurements of light, and then when you look at these three together, you can kind of describe how color is. L, for the purposes of this study, is the most important. L is light to dark. So when you talk about something that's completely black, your color space is entirely dominated by L, because L is dark. So when things are black, it's just dark. So when you talk about color change, you're talking about how far lighter or darker does it get when you start black. So an automotive OEM will want to know the total color change in respect to color. And to get that, they do what is known as DE. So D, when you put that in front of A or L or B, just means change. So the change in L would be DL. And when you talk about DE, so the thing that OEMs will want to know about what's the total color change, that's just the sum, the square root of the sums, or square root of the squares of L, A, and B. So what is the total color change for a black composite? Pretty much you take the absolute value of L, because that's all that really matters in a black color space, is how light or dark you are. So that's the dominant thing. And since you're squaring it and then taking the square root of it, DE is pretty much just the L value. So when I talk about the results in a second, I'm just going to be showing you what is the L value, what is the DE, and I'll explain why I do that in a second. And also at the same time, we looked at gloss measurements, but for the purposes of this presentation, so gloss is how is the actual surface behaving. And for this presentation, just time limitations, I didn't discuss it. But if you want to talk about that with me after the presentation, I feel free to do so. Okay, so jumping right into the results. So there's a lot to kind of take away from this slide. I've put the results from the xenon and QUV testing up on these two charts. So remember, these are the accelerated methods of how can we try and find out how a composite will perform in the field in a quicker fashion than sticking it out in the sun for 2 years. So on the left are the xenon results, and on the right are QUV. The first thing that jumps out to me when I look at this is, so these were measured every 500 hours. So the testing cycle for these two things is to take them out every 500 hours and measure color. So every point is a measurement at 500 hours. And immediately looking to these two charts, I can see that the xenon testing isn't as long. We didn't take as many points for that mode of testing. So that means to me, it's a more intensive test. And then the second thing I look at is there's clear separation, at least in QUV, and pretty good separation when you look at xenon arc of the three different formulations. So I can kind of get a gut judgment that based on the two tests, that Formulation C performed the strongest. It's the green line. I hope you can see it relatively well. But the green line on the bottom for each of the respective graphs is Formulation C. So it gives me an idea, since it had the smallest amount of color change, that it performed the best over time when compared to the three. And then the next formulation is the blue line, which is Formulation A. And so that performed a little bit worse, because remember once again that if you have a bigger number, that means you have a bigger color change. And if you want something to not be, if you want something to stay the same and look the same out in the field, you want it to look the same over time. So you don't want its color to change as it's being exposed to the elements. So Formulation B is the middle of the three. And then Formulation C, we'd say, has the poorest weathering resistance of the three. And what OEMs like to see with respect to DE testing is to have a DE less than 3 after some amount of hours. So that means that after the DE has gone greater than 3, that the color change has come to a point where they don't consider it acceptable. So as you see with Formulation 3, we took it out at there was less data points when compared to the other two formulations. That means that it had reached a DE greater than 3, so we considered the test to be complete for that specimen at that time. And so, and one more thing I want to point out is, so DL is on the bottom of these charts and DE is on the top of these. So if you remember, DL is essentially just the square DE. So DL is going down, is taking on a negative number when we measured it for these formulations. So that means these samples are getting darker over time as opposed to getting lighter, and that's going to be important in a second. So this is just another comparison of the two methods. I fitted them with a straight linear line to get an idea of, is the trend in exposure degradation over time or color degradation over time linear for the two methods. And you can see for QUV and xenon, there's a relatively strong linear fit between the two. So we can somewhat accurately say that after 500 hours, after you get an initial kind of delta of exposure, that the sample degrades at a relatively uniform rate or a relatively constant rate over time. And also you can see, like I mentioned earlier, the slopes of the two lines, or the slopes of the two formulations, the slopes of the three formulations for the two methods, that the xenon has a higher slope than compared to QUV, so it's a more intensive test. So QUV exposure, while will give you a longer period of time that the test will be conducted, but the slope will be slower. So if you're expecting to see more minor differences, it might be the more appropriate method. But if you just want a quick and dirty, what's the best out of these three methods, or what these three formulations, xenon arc appears to be the better tool to use because it gives you clear separation between the three formulations in a smaller amount of time. So before I move on to the outdoor test results, I just want to remind you, these are accelerated methods. So ideally what we're doing here is to test this because we ultimately want to understand how will these formulations perform in the field, which is proven out by outdoor testing. So the first thing I want to point out is let's talk about DE. So what's the total color change over time? And at least in comparison to the relative strength of the three formulations, the outdoor exposure is in agreement with the accelerated methods. So we can see that formulation C has a pretty small color change after 2 years of being exposed in the sun, and it also had the same, so it had the greatest exposure resistance when compared to the other two formulations, like it did for both of the accelerated methods. And then we can see formulation A and B had less of a clear separation when compared to the accelerated methods, where they were clearly defined. There's a difference between the two in their exposure strengths. But one very important thing that I see when I look at these results is I want you to look at DL. So remember earlier I pointed out that the DLs for the accelerated methods were all negative, meaning the samples got darker over time. But here, if you look at formulation B for the DL, it actually has a positive number. So that has a positive trend over time. So what that means is formulation B got lighter, and it had a different failure mode when compared to its accelerated method than for its outdoor method. So on the left, I've showed the completed QUV specimens, and xenon arc look the same, I just didn't have pictures of them. So on the left is QUV specimens that have been exposed to, or have been run through the accelerated weathering test, and then then the samples on the right are the specimens after they completed 2-year Florida exposure. And as you can see, all the samples for QUV exposure got darker, meaning carbon black was kind of exposed on the surface got marred, and as you see the carbon black become exposed, your DE is that blackening effect of the carbon black becoming exposed. But if you look at formulation B for outdoor weathering, you can see that it turned white. So it had a completely different failure mode in comparison to its QUV failure mode. And this is a very interesting finding, because you can imagine if you're a part formulator, you want to know how is your part going to perform out in the field. And it might be acceptable to say, okay, I know eventually these parts are going to degrade, but if it degrades and turns darker, that's acceptable, I'm okay with that. But if it turns white, even if the DE metric is the same for both methods, that's not acceptable because that's going to stand out in my part. Where, you know, if it turns black in an already black composite, yeah, it's not great, and I would rather it stay the same color over time, but at least I can live with that. So this is, it's an important finding, at least to me, because this is not something we were able to find for accelerated methods. So in conclusion, what we took away from this and what I want to kind of give out to the part formulators and people that are designing these parts is when you're working with molding color solutions for composites, you want to focus on just testing as much as you can. You can do accelerated methods and you'll get a good idea, is my accelerated test going to provide a good separation between my different trial formulations? Well, I understand, is my exposure strength getting better as I make X, Y, and Z change? But it ultimately won't tell you exactly how the part will perform in the field. You might get a good idea, will I meet an OEM spec, or will I meet an OEM specification? So if a formulation has a DE greater than 3 or less than 3 at 3,000 hours of xenon exposure or 5,000 hours of QUV exposure, you have a pretty good idea that your formulation will meet an OEM specification, that it will pass OEM qualifications, but you won't exactly know how it will look when the outdoor test is completed. So really what I want to impart to you today is when you're doing accelerated weathering for molding color testing, just make sure that you test as early as possible and do as many tests as possible, because really that's what's going to be needed if you eventually want a part to be adopted. And unfortunately, one of the things that we had intended to do when we started this experimentation is ultimately I get asked a lot, hey Joe, if we have a DE of 2 at 1,000 hours of accelerated weathering in xenon or whatever it is, what's that going to be from Florida? What's the correlation model between all these different tests and all these different methods? And ultimately what we found is that is going to need more work and it's going to need more testing. So if these are sorts of things that you want to answer, make sure that you just test more, because we ultimately found that these 3 tests are disparate enough that you can't say 500 hours of xenon measurements equals 6 months of Florida weathering. That's not something that proved out in our testing. And I'd like to thank our collaboration partners at Automotive and the rest of the Ineos SMC development team. If you have any questions, feel free to ask them. I'll be out in the booth all day. Thank you.
We do have time for some questions.
The question was the resin system polyester or vinyl ester. So traditionally vinyl esters aren't considered all that great because you're putting more aromatic groups in the system, right? So this is a hybrid. I'm not really answering your question kind of intentionally, but it's not vinyl ester, I can tell you that.
So you mentioned that there were 2 different failing modes, right? With the QAV and with the Florida. So can you elaborate on that? Was it, because you said the carbon black got exposed in that QAV, and that's why it turned black, and then the Florida turned white. And is that because of like the degradation in the polymer, or are there different physical mechanisms taking place?
So my speculation is it has to do with just you're getting different wavelengths of light in the sun, you're getting different amounts of humidity, you're getting just different amounts of energy put in the system, so things are happening differently. I don't know the exact mechanism of why that happened. That's glass fiber can be exposed on the surface, so obviously something is degraded enough that it's washing away the carbon black that should be the topmost layer of the composite, but in this case it's no longer there. The interesting thing to me is that the DE is only 3 or whatever it is for that, even though it's completely different, right? So that has the same relative DE, so the same relative color change as any of those other parts, as the one to the left of it, but it looks completely different.
Any other questions?
Just real quick, comment on the controller systems for that.
Just asking if the filler systems were the same across all three packages for the most part, as
They
far
were.
as the extender.
Yeah, so they were different. Formulations B and C had what are they called? The modified low density filler packages. I'm sure you can guess what they are.
Yeah,
Whereas Formulation A has a more traditional filler system,
okay.
but there's some a little bit of proprietariness to that.
You see a dramatic difference between calcium carbonate and ATH in UV testing?
There are differences between the two.
Okay, okay.
Joe, can you speak to the addition of moisture or cycling of moisture? I didn't catch in those test equipment, the QUV, whatnot, what cycle or how you're adding moisture, humidity to the environment versus the flower exposure, the outdoor exposure might have actual humidity and moisture?
Sure. So outdoor exposure, that's just your whatever, it's out in the field, so rain, morning dew, all that. QUV has a condensation cycle, so if I remember correctly, moisture is actually sprayed. It's a spray cycle directly onto the specimens. And so there's different segments, I don't remember them all off the top of my head, but we did follow the actual SAE method for that. And so I believe it's just actual spray is applied directly to the specimen for a specific cycle. And then for xenon arc, it is a humidity where I believe there's both a moisture that comes in from both the top and the bottom of the chamber to give it overall humidity.
Thank you.
Any other questions?